Embeddings are a fundamental part of large language models. Large language models like ChatGPT and Gemini use embeddings to represent words and text numerically. This is a video on embeddings, explained with mathematics simplified. In this video, we will first understand what an embedding is. We will then explore the geometric meaning of embeddings and why higher dimensional representations are needed. Finally, we will use an open-source model to see how embeddings work in practice. Using principal component analysis, we will visualize how words are arranged in the embedding space. Hi, welcome to the video on embeddings, simplified by Maths Simplified.
We know that computers cannot understand words the way humans do. Computers can only understand numbers. So the first step in any language model is to convert words into numbers. For example, consider the text, "Hello World." One simple way to represent this text is using ASCII codes, where each character is mapped to a number. H becomes 72, E becomes 101, so the computer sees "Hello World" as a sequence of numbers. But this representation has a big problem. A computer needs a unique representation for every word and meaning. But in most human languages, a single word can have multiple meanings. Take the word mole, for example. A mole can be an animal, a mole can be a chemical unit, a mole can also be a skin mark. If we represent the word mole using a single number or even a fixed sequence of numbers, the computer has no way to distinguish these meanings. The meaning of a word depends on context, not just its spelling. To solve this problem, we do not represent a word using one number. Instead, we represent a word using a vector. A vector is a list of numbers that lives in a multi-dimensional space. Each dimension captures some hidden property of the word, such as meaning, usage, similarity, or grammatical role. Large language models predict one token at a time based on previous tokens. To do this effectively, the model must organize words in a meaningful way. For example, ant and ants should be close to each other. Rain and storm should point in similar directions. Ant and elephant should be far apart. This organization is possible only when words are placed in a vector space. Let's start with a simple sentence. The battery stores energy, the engine converts energy, and the body needs energy. Here, we are interested in learning embedding vectors for the words battery, energy, engine, and body. Large language models embed all words, but for simplicity, we will focus only on these. The role of embeddings is to place similar words close together and dissimilar words far apart in a vector space. In this example, we have 3 semantic clusters, and the word energy appears in all of them. The embedding should place energy close to every cluster. Now let's see what happens when we try to do this in one dimension. When we move energy closer to one group, it automatically moves away from the others. In one dimension, we are unable to place energy at the same distance from all groups. This is not a training problem, it is a geometric limitation. One dimension is not enough to satisfy our objective. So the natural question is, what if we add one more dimension? Now we move from a line to a two-dimensional space. In 2 dimensions, we have more freedom to arrange the words. The word energy can now move closer to all 3 clusters, but it still cannot be equally close to all of them at the same time. 2 dimensions help, but the objective is still not fully satisfied. Now, Let's add one more word, the word machine. The word machine should be close to battery and engine because engines and batteries are part of machines. At the same time, the word energy should remain close to all semantic clusters, but far away from the machine. In 2 dimensions, trying to satisfy all these constraints becomes difficult. Moving machine closer to battery and engine pushes.
Even for this small sentence, we are unable to perfectly arrange the words in 2 dimensions. Now imagine a real prompt with hundreds of words and many overlapping meanings. This is why embeddings need higher dimensions. When we move to 3 dimensions, the model gains additional freedom to satisfy competing constraints. But embeddings must do more than just organize meaning. What if we mistype energy as energy or energy? A good embedding should place these misspelled words close to energy without disturbing other semantic clusters. Higher dimensions allow small input changes to create small local movements in embedding space. This is how large language models remain robust to noise, typos, and variation while preserving meaning.
Embeddings resolve this by placing each meaning in a different region of the vector space. Which meaning is used depends on context. This is why embeddings are geometric. This table shows the size of the embedding space for popular models that are publicly available. Let's try to understand how large language models treat embeddings using Distilbert. In this example, we give simple words like hello, hi, and hey to a pre-trained Distilbert. Distilbert converts each word into a numerical vector with 768 dimensions. When we print the embedding shape, we see something like embedding shape equals 9 by 768. Next, we compute cosine similarity between these vectors. Cosine similarity measures how closely 2 vectors point in the same direction. A value close to 1 means the meanings are very similar. For example, the cosine similarity between hello and hi is very high, typically around 0.9. This tells us that Distilbert has learned that hello and hi appear in very similar contexts and therefore live close together in embedding space. On the other hand, words like hello and car have a much lower similarity. Their vectors point in very different directions, meaning the model considers them semantically unrelated. To visualize this, we reduce the embedding dimension from 768 down to just 2 using principal component analysis. In this 2-dimensional plot, similar words form clusters. Greetings like hello, hi, and hey appear close together, while animals, vehicles, and other concepts form separate groups. During training, embedding vectors are learnable. The model sees large amounts of text, makes predictions, and updates its embeddings using gradients. Inference is what happens after training is finished. In inference, the model does not learn or update weights. When you type a prompt into ChatGPT, the model simply uses its pre-trained embeddings and transformer weights to generate an output. The embedding vector for a word stays fixed, but attention combines embeddings differently depending on the input. In short, training builds the embedding space, and inference uses it. To summarize, embeddings represent words as points in a vector space. Higher dimensions allow overlapping meanings to be separated geometrically. This is why embeddings are central to large language models. Thank you for watching.